So the first thing that we're going to do today is take a look at in-class assignment number 15. So this, I don't recall whether or not you were ever assigned any in the homework sets, but this might be the first problem that you face where we have two energy storage elements. So let me take just a moment to switch things over here. All right, so how are these two inductors connected? They are in parallel. All right. So that means I'm going to replace those two inductors with a single equivalent inductance, right? So what's that equivalent inductance going to look like? So 0.75 Henry. Absolutely. All right. So I'm going to erase the two inductors that I have. And replace them with a single equivalent inductance. So really, I just need something connected between this node and this node. So I'm going to choose to represent it diagonally. It doesn't particularly matter. Oops, that's not what I wanted to do. So 0.75 Henries. And then we need to arbitrarily choose a direction in which our inductor current is going to flow. Because since this is a transient analysis problem containing an equivalent inductance, we obviously need to pay attention to what the inductor current is doing at t is equal to 0 minus, so that we know how to analyze the circuit at t is equal to 0 plus. So I'm going to choose my inductor current to be flowing diagonally down like so. So we're going to call this IL of t. All right, so we've simplified the circuit as much as possible presently. We have converted our two energy storage elements into a single energy storage element so that we can see that this is indeed a first order transient analysis problem. So let's get to our analysis. So let me switch over here. So at t is equal to 0 minus, go back over here. Our inductor is going to look like a short circuit and our switch is open. So I'm going to redraw this guy. I'm not mistaken, that was a 10-volt source, 4 ohm resistor. I believe I have a short circuit here. 5 amp source direction up. Over which we have the voltage VCS of t, which is our quantity that we are actually interested in. 4 ohm. Right here. Six ohm resistor right here. Our inductor is going to look like a short circuit. Here is our inductor current, IL of 0 minus, and excuse me, this should be VCS at 0 minus. And then I believe it's a 12 ohm resistor on the right. Yeah. All right. And our goal here is to solve for VCS at 0 minus and IL at 0 minus. So what's something that we can observe to help out our analysis here? So the 6 ohm resistor and the 12 ohm resistor are in parallel with the short circuit that is representing the inductance, which means they will contribute absolutely nothing. So I'm just going to cross them out. They should not be part of our analysis. That is a good observation. All right. So how could we go about finding either VCS or IL? Nodal analysis seems reasonable here. Yeah. If we didn't want to use nodal analysis, or if we didn't want to set up a system of equations, I guess would be a better way to put this. I believe we could use superposition to split this up into two easy things to analyze and add the results together, but the system of equations that we're going to use isn't particularly difficult either, so nodal's probably fair. Isaiah, what's up? Could you repeat the question, please? Mhm. Absolutely. Mhm. All right, so Carson, I believe, suggested nodal analysis, so let's use that. So I'm going to choose my bottommost node to be ground. Let's call this VA, this VB, and I believe those are the only nodes I have. So if we can see by inspection that VA is just equal to 10 volts. Applying Kirchhoff's current law at node B, we are going to have VB minus VA over 4 ohms minus 5 amps plus VB divided by 4 ohms is equal to 0. Solving this system of equations, we will find that VA is obviously 10 volts. And I can't do this in my head, so let me throw it into my calculator. So I'm doing this as a 2x2 system because I am indeed that lazy. So my first equation is 1 VA plus 0 VB is equal to 10. My second equation is negative 1/4 VA. 1/4 plus 1/4 would look like 1/2 VB. My constant term will be 5 amps. Solving, I get VB to be 15 volts. So now that I know those two things, how can I solve for VCS and IL? Yes. So Cameron, I believe, asked if VCS is just VB. VCS is indeed equal to VB because the positive polarity terminal of our voltage VCS is at node B, and the negative polarity terminal of our voltage VCS is at ground. So VB minus 0 is equal to VCS. So VCS at 0 minus is just VB is 15 volts. How do we find IL at 0 minus? Absolutely right. Just good old Ohm's law. Does anyone have any questions, comments, or concerns about our analysis at t is equal to 0 minus? All right. So at t is equal to 0 plus, our switch is now going to be closed. So I'm redrawing my circuit. I'm going to replace my inductor with a current source having the same value, or excuse me, same magnitude and direction as IL at 0 minus. So I believe that would be this direction with a magnitude of 15/4 of an amp. And the quantity that I am most interested in finding is just VCS at 0 plus, because we know that IL at 0 plus must be equal to IL at 0 minus, or 15/4 of an amp. So what circuit analysis method would you guys prefer to use to find VCS in this case? So since no one is suggesting anything, I personally would do nodal analysis here, because there are 4 meshes, which will be problematic depending on the type of calculator that I have. I believe there are only 1, 2, let's see, 1, 2, 3, 4, 5 nodes, one of which will be ground, but because I have a voltage source, one of those nodes will be a known voltage. So if I chose my ground to be here, let's call this node VA, and I'm going to highlight it just so we're all on the same page here. This is my node VA. Oh, I might have overcounted my nodes. This guy is going to be VB. This guy is going to be ground. And just for the sake of argument, I'll highlight this one up here, but we know that its value is just 10 volts. So I'm just going to write it as 10 volts in my equations. So this is VB. So when we're doing KCL at node A, we're going to be adding this current, this current, this current, this current, and this current together. So KCL at A is going to look like VA minus 10 volts over 4 ohms. That's the current flowing to the left. Minus 5 amps. That's the current flowing down. Plus VA minus VB over 4 ohms. So that's the current flowing to the right. Plus VA minus VB over 6 ohms. That's the current flowing down through the 6 ohm resistor. Plus VA over 12 ohms, current flowing down through the 12 ohm resistor, is equal to 0. KCL at B, I'm going to add this current, and this current together. So that's going to look like VB minus VA over 4 ohms. Plus VB minus VA over 6 ohms. Plus 15/4 of an amp is equal to 0. Solving this system will give me VA and VB. So let's throw that into our calculators. So solving this as a 2x2 system, my coefficient for VA in my first equation is 1/4 plus 1/4 plus 1/6 plus 1/12. My coefficient for VB is negative 1/4 minus 1/6. My constant term is going to be 10/4 plus 5. You're whispering, did I make a mistake? Okay. In my second equation, my coefficient for VA is going to be negative 1/4 minus 1/6. My coefficient for VB will be 1/4 plus 1/6. And my constant term will be negative 15/4. Solving for VA, I get 45/4 volts. And VB is 9/4 volts. Using these pieces of information, VCS at 0 plus would be equal to what? Yeah, so just VA in this case, which is 45/4 of a volt. All right. Anybody have any questions about our analysis here at t is equal to 0 plus? Okay. So moving on to t is equal to infinity. At t is equal to infinity, we are always at DC steady state. So that means our equivalent inductance is going to look like a short circuit again. So drawing my circuit. Here's what we are dealing with. How would we most easily find VCS? Probably nodal analysis again, absolutely. So using the bottommost node as ground, just going to run through here and identify things really quickly to make sure we don't make any simple mistakes. So that's my ground node. So when we perform KCL at node A, we are going to have current plus this current plus this current plus this current plus this current. So it's going to be VA minus 10 volts over 4 ohms. Excuse me, minus 5 amps. Plus VA over 4 ohms. Plus VA over 6 ohms. Plus VA over 12 ohms is equal to 0. Solving this one equation for VA, I'm going to throw it into my numerical solver on my calculator really quickly. So x minus 10 over 4 minus 5 plus x over 4 plus x over 6 plus x over 12 is equal to 0. I'm just going to put a guess value of 0, solve for x. Calculator is thinking about things. Yep. Give me just a second and I will explain how I would solve for the IL. So I got VA to be equal to 10 volts here. All right. So if I had wanted IL, which would have been this current here, let's call it IL at infinity. Using Kirchhoff's current law at this node, we could see that IL would just be the current flowing from left to right through the 4 ohm resistor plus the current flowing down through the 6 ohm resistor. So that would be VA over 4 plus VA over 6. Yep. All right, so since VA is 10 volts, VCS at infinity is just VA is just 10 volts. Anybody have any problem with the analysis that we did here? Nobody's saying anything, so I'll assume you're all catching what I'm throwing. So our fourth step here is going to be to calculate our time constant. So recall from the very beginning of the problem that we found the equivalent inductance to be 0.75 henries, which we got by combining those two inductors in parallel into a single equivalent inductance. To find our equivalent resistance, we're going to redraw our circuit. This has to be during the transient condition, which means our switch is closed. Oops, I missed the 6 ohm resistor that goes here. My apologies. Perhaps that was the whispering. All right, so this is what my circuit looks like during the transient condition. When I'm trying to find my equivalent resistance, this is the Thevenin equivalent resistance seen by our energy storage element. So that means I take my 0.75 Henry inductor out. Since I'm looking for an equivalent resistance, I need to look at a dead network. So I'm going to turn my 5 amp source off. And I'm also going to turn my 10 volt source off. So this is the network that I'm finding the equivalent resistance of. I can't really do this by inspection, so I'm going to identify my nodes. So I have this node right here. This node right here. This node right here. I'm going to call this terminal A, this one B, and the red node C. And I'm trying to find the resistance seen between A and B because those are the terminals where my inductor was before I took it out. So putting A on the left-hand side of the circuit and B on the right-hand side. To go from A to literally anywhere, we have to go through C. So to go from A to C, we can go either through the 4 ohm resistor or the 6 ohm resistor. So we're going to see 4 in parallel with 6. That 4 doesn't look particularly legible, so let me fix that. To go from C to B, we can go through the 12 or we can go through the other 4. So let's see. 4 in parallel with 6 is going to be 24 over 10. So this looks like 2.4 ohms. 12 in parallel with 4 is going to be 48 over 16, which looks like 3. So REQ is 5.4 ohms. Tau is LEQ over REQ. So 0.75 divided by 5.4. That gave me a number that it's fine, 0.13 and then 8's repeating, but I would prefer a fraction. So let me think about this. 3/4 divided by, let's see, 5.4 is 5 2/5. So that would be 52/5. No, 27. So 5/36 of a second. The inverse of tau would then be 36/5 per second. And from here, we simply put everything together. So VCS as a function of time is going to be the value that we had at 0 minus, which let me scroll up here and find it because it's been a hot minute. 15 volts. For t less than 0 minus. Then we're going to have VCS at 0 plus, which I believe was 45/4. At t is equal to infinity. I believe it was 10. I'm going to write 10 as 40 over 4. E to the minus, the inverse of tau was 36/5 t plus 10 volts for t greater than or equal to 0 plus. 45 minus 40, so this looks like 5/4 or 1.25. So just for the sake of argument, let's see if things check out. 15 volts checks out. 5/4, 36/5, 10 volts. It looks like we did everything correctly. So this realistically would be the hardest type of thing I might ask you on your exam. Now, I do want to give you guys a heads up. Web work assignment number 15, which is the one that's opened up today. The circuits in there are large and convoluted. For if anybody has looked at it, you'll see what I mean. In my opinion, the homework set number 15 is more practice for nodal and mesh than it is for actually transient analysis stuff. So I'm not encouraging anybody to not do it, because more practice on any type of circuit analysis is always good. But if there was a single homework assignment that I was going to skip, it would be homework set number 15. Just because it's more practice for nodal and mesh than it is for actually doing the transient analysis stuff. Jason.
So a better use of time would be to print out a practice exam and do that instead of spending all your time banging your head against the wall on before surgery.
Not going to record myself responding to that.
Fair enough. Fair enough.
It is, yes, it is still technically part of your homework grade. So I want to be clear about that. I'm not saying don't do it. You will still be scored on it. That being said, you have 24 homework assignments, and so one of them isn't going to make a huge impact on your grade. That's all I'm going to say about it. Okay. Walker, I believe you had your hand up. Same. I think I've answered it. Okay. So what we have left for the rest of this class meeting is the lab. So before you guys get started on that, I want to mention a couple of things. Okay. I believe this is the first lab assignment where we are not going to be using the DC power supply. Instead, you are going to be using the function generator as well as the oscilloscope. This cable right here is your function generator leads. Okay, so it has a BNC cable on one side or BNC connector on one side, and then it has a pair of alligator clips on the other side. This is what connects your function generator to your circuit. So this is how you're applying your time varying signal to your circuit of interest. This is an oscilloscope probe. Okay. It also has a BNC connector on one end, but it looks significantly different than the other one. This one is encased in plastic for whatever reason. This bit right here slides down, leaving behind a hook, okay? And then this bit right here is going to be your ground connection. So think about this as the positive polarity terminal for the time varying voltage you're measuring. This is the negative polarity terminal for the time varying voltage you're measuring. Oscilloscope probes are only used for measuring things. If you hook it up to your function generator, it will not work. Okay. So this is what connects your oscilloscope to your circuit so that you can see what is going on. Another thing that I want to point out here is that there's this little red switch, and you can slide it back and forth. It needs to be on the 1x setting, not the 10x setting. Otherwise, your numbers will be garbage. So just make sure that this red switch is slid upwards towards the tip as opposed to downwards towards the cable. And it also literally has printed on here 1x and 10x. We want the 1x setting. Okay. All right. So just wanted to clarify a couple of things since this is likely most of you guys' first time using these pieces of equipment. And it drives me insane when I see people use the wrong wires for the wrong pieces of equipment. So now you know which ones are which. Don't screw